Welcome to UPSC Study Academy, empowering aspirants and shaping futures. In this episode, we'll explore the nature of electromagnetic waves, amplitude modulation, and frequency modulation. What exactly are electromagnetic waves? Electromagnetic waves are generated when an electric charge, such as an electron, accelerates. This acceleration causes a disturbance in the surrounding electric and magnetic fields, creating waves that radiate outwards from the source. Common sources of electromagnetic waves include antennas used in communication systems, which convert electrical signals into electromagnetic waves. It is mainly used in space communication. And how do these waves travel? Do they need something to move through, like sound needs air? Unlike sound waves, electromagnetic waves don't need a medium to travel. They can move through a vacuum, air, and other materials. This property is crucial for communication systems, enabling signals to be transmitted over vast distances, including between Earth and satellites in space. Speaking of traveling, how fast do these waves move? In a vacuum, electromagnetic waves travel at the speed of light, which is about 299,792 kilometers per second, or roughly 186,282 miles per second. When they pass through materials like air, water, or glass, their speed decreases slightly because of the material's refractive index. But can these waves be deflected or changed in any way? Electromagnetic waves can be deflected by several factors. They can be reflected when they hit a surface, like how radar waves bounce off objects. They can also be refracted or bent when they pass from one medium to another, like from air to water. Additionally, they can be diffracted, which means they bend around obstacles or spread out after passing through small openings. Lastly, they can be scattered when they encounter particles or irregularities in a medium. What about the range of wavelengths for electromagnetic waves? Electromagnetic waves cover a broad spectrum of wavelengths and frequencies, known as the electromagnetic spectrum. It includes radio waves, wavelengths from about 1 millimeter to 100 kilometers, used in radio, TV, and cell phones. Microwaves, wavelengths from 1 millimeter to 1 meter, used in radar, satellite communications, and microwave ovens. Infrared waves, wavelengths from about 700 nanometers to 1 millimeter, used in remote controls and thermal imaging. Visible light, wavelengths from about 400 to 700 nanometers, which we can see. Ultraviolet light, wavelengths from about 10 to 400 nanometers, used in sterilization and fluorescent lighting. X-rays, wavelengths from about 0.01 to 10 nanometers, used in medical imaging. Gamma rays, wavelengths less than 0.01 nanometers, used in cancer treatment and nuclear physics. Understanding the different radio frequency bands, their ranges, and applications is essential for grasping how various communication systems operate. Each band has unique properties that make it suitable for specific applications, from deep-sea communication with submarines to high-speed data transmission via satellite. Let's start with the extremely low-frequency, ELF, band. Frequency range, 3 Hz to 30 Hz. Applications. ELF waves are primarily used for communication with submarines because they can penetrate deep into water. Due to their long wavelengths, ELF waves can travel great distances and through dense materials. Next, we have the very low frequency, VLF, band. Frequency range, 3 kHz to 30 kHz. Applications. VLF waves are used for long-distance communication and navigation services, especially for military purposes. They can also penetrate water, making them useful for submarine communication. Moving on to the low-frequency, LF, band. Frequency range, 30 kHz to 300 kHz. Applications. LF waves are used for maritime navigation, aviation communication, and AM radio broadcasting in some regions. These waves can travel long distances and through obstacles like buildings and trees. Now, let's look at the medium frequency, MF, band. Frequency range, 300 kHz to 3 MHz. Applications. MF waves are primarily used for AM radio broadcasting, specifically in the range of 530 kHz to 1,700 kHz, and for maritime communication. They can travel over moderate distances, especially at night when atmospheric conditions allow for better propagation. The high-frequency, HF, band is next. Frequency range, 3 MHz to 30 MHz. Applications. HF waves are used for shortwave radio broadcasting, amateur radio, and international aviation communication. They can reflect off the ionosphere, allowing them to reach distances far beyond the horizon. Let's discuss the very high-frequency, VHF, band. Frequency range, 30 MHz to 300 MHz. Applications. VHF waves are used for FM radio broadcasting, television broadcasts, two-way LAN mobile radio systems, long-range data communication, and air traffic control. They offer a balance between range and quality, providing clear signals over relatively long distances. Now, we have the ultra-high frequency, UHF band. Frequency range, 300 MHz to 3 GHz. Applications, UHF waves are used for television broadcasts, mobile phones, satellite communication, GPS, Wi-Fi, and Bluetooth. These waves can carry large amounts of data and are suitable for urban environments due to their ability to penetrate buildings. Finally, let's look at the super high frequency, SHF band. Frequency range, 3 GHz to 30 GHz. Applications, SHF waves are used for radar, satellite communication, microwave links, and Wi-Fi. They provide high data rates and are essential for modern communication technologies, although they require line-of-sight propagation. How do we use electromagnetic waves to transmit information via broadcasting? We'll explore two key methods: amplitude modulation, AM, and frequency modulation, FM. Let's start with amplitude modulation. But first, what exactly is modulation? Modulation is the process of varying a property of a carrier wave to transmit information. In the case of AM, it's the amplitude of the electromagnetic wave that is varied. Amplitude modulation involves changing the amplitude, or height, of the carrier wave in proportion to the information signal, such as an audio signal. What are the two types in AM waves? Carrier wave, a steady wave with a constant frequency and amplitude. Modulating signal, the information signal that you want to transmit. When you modulate the amplitude of the carrier wave, according to the information signal, you get an AM signal. The carrier's frequency remains constant, but its amplitude varies in line with the amplitude of the input signal. Applications of AM. Radio broadcasting. AM radio is commonly used for broadcasting news, talk shows, and music. Aviation communication. AM is widely used in aviation for voice communication due to its longer range. AM waves can travel long distances, especially at night when atmospheric conditions are favorable. However, they are more susceptible to noise and interference because both the signal and the noise affect the amplitude. Let's talk about frequency modulation, FM. How does FM differ from AM? In frequency modulation, it's the frequency of the carrier wave that is varied in proportion to the information signal, while the amplitude remains constant. How FM works? In FM, the carrier wave's frequency changes in line with the amplitude of the input signal. When the amplitude of the input signal increases, the frequency of the carrier wave increases, and vice versa. Applications of FM. Radio broadcasting. FM radio is known for broadcasting high-fidelity music and audio. Television sound. FM is used for the audio component of television broadcasts. Two-way radio systems. FM is used in police, fire, and emergency services communication for its clarity and reliability. Here's a comparison table highlighting the differences between amplitude modulation, AM, and frequency modulation, FM. Don't forget to like, share, subscribe, and hit the notification bell so you won't miss the next part of our series on communication systems. Thanks for watching.